Assalamu alaikum dear students, welcome back. We are now in part 2 from chapter 5, sound energy. In this part we should determine the sound intensity at a specific point, and we want to define the threshold of hearing and the threshold of pain. Don't forget that we defined last time the acoustic sound energy, which is the energy carried by the sound, and we also defined the acoustic power of a transmitter as the energy it provides to the surrounding environment per unit of time, and it's given by P equal E over T. When moving away from a sound source, the sound is received weaker. Why does this happen? And how does physics explain this phenomenon? This is what we want to explain in this video. First, consider a point sound source O which emits sound in all directions with a power P. Don't forget that the power is the energy emitted by the source O during a unit of time. In our study, we consider that sound propagates with the same speed in all directions, so the wavefronts formed necessarily take the spherical shape. Second, the propagation medium does not dampen the sound, which means that does not absorb the sound energy emitted. Then each wavefront receives the same power P produced by the source. In addition to this, power is distributed uniformly over the surface of the spherical wavefront. But what does it mean that the power is distributed evenly over the surface of the spherical wavefront? To understand better, we take a single sphere. It is the sphere of radius r2 with surface s2, and which completely receives the power from the source. Since the power is equally distributed over the spherical surface of a wavefront, we conclude that if a sound receiver occupies half of the sphere, it will receive half of the power P. If another receiver occupies a quarter of the sphere, it will receive a quarter of the power P. We deduce that the ratio of the receiving surface to the total surface is equal to the ratio of the received power to the total power. This equality of ratios certainly reflects the rule of 3. Okay? This if we were talking about certain surface receiving acoustic power. But what being at a different distance from the source? First, we notice that experience shows that the two identical microphones A and B at the same distance from the source receive the same loudness, which means that A and B receive the same intensity of sound because they are at equal distances from the source, and the sound intensity received by C is greater than the sound intensity received by D because C is closer to the source. To deal with this phenomenon, we need to define a new physical quantity, and they call it acoustic or sound intensity I, which is equal to the sound power received per unit area placed at a point perpendicular to the direction of the propagation of the sound wave. Note that a microphone like the human ear has a receiving surface S. Microphones A and B have the same receiving surface, I mean their heads, and are located on the same sphere as S2, so they receive the same portion of the power P, which means that P of A equal to P of B. This gives that I of A is equal to P received by A over S, which is also equal to P received by B over S, which is equal to IP. This result is consistent with experience. So until now, this magnitude is valid. We will examine this magnitude on the other two microphones. The microphones C and D always have the same receiving surface, but D is further from the source. In addition, the power P is distributed over S3, which is greater than S2, so the part received by the receiving surface of D is lower than that received by the receiving surface of C. Then P of C is greater than P of B, and I of A, which is equal to P of C over S, is greater than P of B over S, which is equal to IB. Again, this result is in agreement with experience, and this magnitude succeeds once again in explaining the phenomenon. Now, after defining the sound intensity, let's practice. We have a point source S emits a sound wave of power P equal to 2 watt. At distances D1 4 meter and D2 8 meters of S, the sound is distributed over two spheres of respective areas, A1 201 meters squared and A2 804 meters squared. First, let's determine the intensity of the sound at each distance D1, then D2. As we know that the sound intensity at point 1 is equal to the power emitted by the source over that surface area that receives this power, which is 2 watt over 201 meters squared, which is equal to 0.0099 watt per meter squared. Same as the second surface area, I2 is equal to 2 watt over 804 meters squared, which is equal to 0.00248 watt per squared. Now we should verify that when D2 equal to 2 multiplied D1, then I2 is equal to I1 over 4. As it's obvious, D2, which is 8 meter, is double of D1. So if we compare the intensities that we calculated right before, we will find that I2 is quarter I1. You can pause the video for a while to ensure this result. Another application can be solved to deal more with the previous formulas. The same point source S emits a sound wave of power P, 2 watt, but now a microphone of surface area Sm is equal to 20 centimeters squared is placed at a distance r equal to 20 meters from the source. First, we should determine the power received by the microphone. Second, the sound intensity received by it. Concerning the power received, we reached before to the formula that relate the three terms, which are P and the surface area of the receiver and the surface area where the receiver is, which is PR equal to P multiplied by Sm over the surface area where the receiver is, which is 4 pi r squared. If we replace each term by its value, we will get the received power. And notice here, to convert centimeter squared to meter squared, we should multiply by 10 exponent minus 4. Now also apply the formula that we took to calculate the sound intensity, I equal to P over 4 pi r squared. We will get that the sound intensity is 4 times 10 exponent minus 4 watt per meter squared. Okay, it's known that the human ear has certain hearing limits concerning the frequency at which sounds of frequencies between 20 and 20,000 Hz are heard. However, the ear does not hear sound if its intensity is lower than a value called the threshold of hearing, and it begins to feel pain if the sound intensity exceeds a certain value called the threshold of pain. So here we will define the threshold of hearing I0 as the minimum sound intensity at which the ear begins to hear, and the threshold of pain Imax as the maximum sound intensity at which pain is felt in the ear. And notice that the threshold of hearing I0 and the threshold of pain Imax vary with frequency, person, and his age. For example, a frequency of 1000 Hz, the standard values are threshold of hearing I0 10 exponent minus 12 watt per meter squared, and the threshold of pain is I equal to 1 watt per meter squared. Okay, now let's practice about what we took in the last slide. The sound intensity is 2 watt per meter squared at a distance 3 meter. We should calculate the minimum distance from the source without causing hearing damage, knowing that the threshold of pain is I max equal 1 watt per meter squared. So first we will calculate the intensity of sound at distance 3 meters, which is P over 4 pi r squared. And we know that the maximum intensity contains the minimum distance, which we will call it R minimum. So I max equal P over 4 pi R squared. So by putting I max over I1 and replacing I max, I1, R1 by their values, we will find that R minimum is radical 18 meter. Okay guys, for here we finish this video. I will sum up what we took in it. First, the sound intensity is the sound power received per unit area placed at a point, and I equal P equal 4 pi r squared. Second, the sound intensity at a point is the sound power received per unit area of perpendicular to the direction of propagation of the sound at the given point, such that I equal power received over the receiver. Third, for a frequency of 1000 Hz, the standard values are threshold of hearing I0 equal 10 exponent minus 12 watt per meter squared, and the threshold of pain is equal to 1 watt per meter squared. Thank you guys for listening and watching, and pay attention to yourself, and goodbye.